Okay, this is repeated linear factors, example 3. So here is our original integral. Take a look at that factor denominator and decide how many fractions you will need. We'll need a fraction with a denominator of x minus 1. And for this, the cube of x plus 2, we will need 3 fractions in total with exponents of 1, 2, and 3 respectively on x plus 2. So it will look like this. Exponent of 1, 2, 3, and yes, I started with x minus 1. So we need 4 fractions in total. So next we're going to get ourselves that common denominator. It will be this, of course. And we're gonna figure out our numerator. So A has x minus 1 under it only. So it requires x plus 2 all cubed plus B. B has x plus 2 under it. So it needs an x minus 1 factor and also 2 more of the x plus 2 factors. On to C. C has x plus 2 all squared. So it requires multiplication by x minus 1 and 1 x plus 2. Lastly, D. With a denominator already of x plus 2 all cubed, we are missing only x minus 1 here. Okay, now we make our large equation, which actually isn't going to fit on one line because I need to set this original numerator equal to this new numerator. So unfortunately, I'm going to have to stretch this into 2 lines. Okay? Now we begin by using any roots present. So to figure out your roots, you can be looking at these denominators or these ones, right? They're all gonna have the same roots. The only values will be x is positive 1. So if x minus 1 is equal to 0, then x equals positive 1. In here, if x plus 2 equals 0, then x is negative 2. So the only roots are x is positive 1 and x is negative 2. So we'll begin like that. That'll allow us to solve for 2 of the letters. Okay, so first you would substitute x equals 1 into the left side wherever there is an x. You would get 54 on the left side. Now on the right side, if we substitute 1, we're gonna have a times 3 cubed, or a times 27. The other terms, if I put a 1 here, a 1 here, a 1 here, the other terms will all be 0. So we find immediately that a is 54 divided by 27, or 2. Substitute negative 2. You have to be very careful here, substituting a negative number. Make sure you put it in a bracket before raising it to these exponents. You should get 9 on the left side. Now, negative 2 here will give me 0. Same thing here and here. The only non-zero term will be at the end. D times, and it's negative 2 minus 1, or negative 3, from which D is found by dividing 9 by negative 3. Now I'm out of roots, so I've only figured out 2 things. So we can't go to an arbitrary value yet because we still have two unknowns. B and C are both unknown. So we look at coefficients. And often it works to use the highest power. The highest coefficient existing in either the right or the left side is the coefficient of x cubed. On the left side, we have 3x cubed. Now on the right side, we have to determine where we will have x cubed terms. We will have one here if this were expanded. See, x cubed. And preceding it is a, so we have ax cubed. But is that the only place where we would have ax cubed? Sorry, is that the only place we would have an x cubed term? No, there would be one here as well, because this is x squared multiplied by x. So this is x cubed preceded by b. So yes, here, right here, we do have ax cubed, but here also bx cubed. So it's ax cubed plus bx cubed. Nowhere else will we have a cube. This will get up to a square. Here we just have an exponent of 1 on x. Okay, so this is a little tricky, but hopefully you can see we will definitely have ax cubed plus bx times x squared. Okay, now why is this going to help us? Again, because now we have this equation. A plus b is 3, and we already know a is 2. So we can subtract 3 minus 2 to get 1, so b is 1. Now that you only have one unknown and it's c, you could choose to substitute an arbitrary value. The arbitrary value we're going to substitute is 0. It's the easiest one to evaluate, and we have not yet used it up. So we should do this. We should say we already know a is 2, and d is negative 3, and b is 1. Now we're going to substitute x is 0. In the left side, if we do that, we will get 15. Let's go to the right side. We have 2 times, with a 0 here, we're going to get 2 cubed. So 2 times 8 plus 1. We're putting a 0 here, so that's negative 1. And with a 0 here, 2 squared, or 4. Plus c. We're putting 0 here, so negative 1. 0 here, so 2. On to the end, minus 3 times, we're putting 0 here, so that's negative 1. Okay, from which we get 16 minus 4 minus 2c plus 3. And this then becomes negative 2c. And for the number, we have 16 minus 4 plus 3, which is 15. And solving this for c, we're going to have actually 2c is equal to 0. And that means c is 0 after all that. So finally, we have our values. So 2 values determined by the 2 roots. The third value solved using the method of coefficients. And the last one by choosing an arbitrary value for x. The values a, b, c, and d are now substituted here. So we won't have to integrate this term since c is 0. So what are we going to integrate? We have to integrate 2 over x minus 1 plus 1 over x plus 2 minus 3 over x plus 2 all cubed. So they resulted when I substituted a 2 here, a 1 here, a 0 here, and a -3 here. Okay, you should be able to tell these will be logarithmic. The exponents down here are 1. This one will not be logarithmic. To integrate this term, we need to first write it like this. Okay? Now we're going to integrate the terms. Again, a u substitution here is overkill because this would be u, x plus 2. Its derivative is 1. Okay, so we don't need to use a u substitution. I'll just move this up and we will continue. Okay, so the integral of the first term is 2 ln x minus 1. The integral of the second term is 1 times the ln of x plus 2. And in integrating the last term, we will add 1 to the exponent and we will divide by that new exponent. We will add a plus c. We're going to combine these two logarithms. Remember, to combine them, we have to move this coefficient first. So it's going to be x minus 1 all squared. Here, we have positive 3/2, and we can write it with a positive exponent as well. And lastly, combine those logarithms for our final result. Since this is addition, there will be multiplication in the argument of the logarithm. Okay, and at that point, the example is complete.